Chemical kinetics, reversible reactions. Here is a chemical reaction where in the forward direction, one molecule of A collides with one molecule of BC to create a molecule AB plus atom C. So in the forward direction, we have A plus BC yields AB plus C. In the reverse direction, we have AB plus C yields A plus BC. Since it's a reversible reaction, we write it as an equilibrium. Writing the equilibrium is signified by the double arrow. So this tells you this is a reversible reaction and it's going to reach equilibrium. What does equilibrium mean? It simply means that the rate in the forward direction equals the rate in the reverse direction. Let's look at what a rate law is. A rate law says the rate, R, equals a constant, K, times the concentration of each reactant raised to some power. So, since this is a bimolecular reaction where one atom of A collides with one molecule of BC in order for the reaction to happen, M and N are 1. And so the rate in the forward direction equals K times the concentration of A times the concentration of BC. And the rate in the reverse direction equals K reverse times the concentration of AB times the concentration of C. So now, at equilibrium, the rate in the forward direction equals the rate in the reverse direction. So I can say K forward times the concentration of A times the concentration of BC equals K reverse times the concentration of AB times the concentration of C. We'll come back to that. A reaction coordinate diagram is a graph that has energy on the y-axis and progress of the reaction, that is reaction coordinate, on the x-axis. A generic reaction coordinate diagram has the energy of the reactants near the left-hand side and the energy of the products on the right-hand side. And then there's a pathway with a hump to get over. The energy difference between the reactants and the peak is called the activation energy. The larger the activation energy is, the slower the reaction because a smaller fraction of collisions have enough energy to break the bonds on the reactant side. The difference in energy between reactants and products, that is the energy of the products minus the energy of the reactants, is the delta E of the reaction. Sometimes we use delta H for that as well. That's just the energy difference or the enthalpy change. This reaction has a positive delta H because the products are at higher energy. than the reactants. So in this case, delta H being greater than 0 means this is an endothermic reaction. You have to put in heat to drive it. Okay, and let's talk about the specific reaction that we were using before. So on the reactant side, we have atom A and molecule BC. Up here at the very top, we have what's called a transition state. We symbolize that with this double dagger symbol. And in the transition state, the bonds that are going to break are halfway broken. The bonds that are going to form are halfway formed. This particular transition state looks like this. Atom A with a bond to B that is halfway formed, and atom B with a bond to C that is halfway broken. Oh, and actually, it should look like this. And we'll change the color of those two bonds. So this is forming, and this is breaking. Which leads us to the products, AB plus C. So what's the rate in the forward direction again? It is the rate constant times the concentration of A times the concentration of BC. Basically, it's the rate constant times the concentrations of the reactants. In the reverse direction, RR, that equals the rate constant in the reverse direction, Kr, times the concentration of the products, AB plus C. So what happens to these relative rates? Well, when we start out, we have molecules of A and B. We have atoms of A and molecules of BC. Reactant molecules are present, but we don't have any products. The concentrations of these equal 0. So when we start out, the concentrations of reactants are as high as they're going to be. Our rate in the forward direction starts out as fast as it could possibly go. Our rate in the reverse reaction starts out at 0. So here I've frozen my simulation so you can see what's going on. I have 1, 2, 3, 4, 5, 6 A molecules represented by the golden spheres. And a B atom is pink and a C atom is silver. So I have 1, 2, 3, 4, 5, 6 BC molecules. Alright, now I'm going to run this simulation. I'm going to raise the temperature. So now it's really high. We should start seeing some reactions, and we have. If I pause it right now, you can see, look, I have 3 molecules of AB and 3 molecules of BC. I also have 3 A atoms and 3 C atoms. So now the reaction's going in both forward and the reverse direction. And it has equilibrated. Over time, we're probably not going to see a big change in concentration. Even though reaction is taking place, it's happening in both the forward direction and the reverse direction simultaneously. If I pause, I now have 1, 2, 3 4 AB molecules and 1, 2 BC molecules, 2 free A atoms, and 4 free C atoms. That doesn't make sense. I guess I had just paused the simulation in the middle of a collision. This looks more reasonable. I have 1, 2, 3, 4 free A atoms and 2 free C atoms now. Okay, so yeah, over time, the average concentration of reactants and products is staying the same. We've reached equilibrium. Let's look at what's happening as a reaction reaches equilibrium. We have rate of reaction on the y-axis and time elapsed on the x-axis. Let's consider the very beginning of the reaction, here and here. For the forward reaction here, we have a very high reaction rate. That's because the concentration of A and BC are high. Now, recall also that the rate in the reverse direction equals another rate constant times the concentrations of the products. And right here where we're starting, the concentrations of products, A, B, and C, equals 0, because we only put reactants in our reaction vessel. As time goes on, say at this point, we can see that the rate of the forward reaction has gone down by this much. That's because as the reaction progresses, the concentration of A and the concentration of BC go down. Right, so I'm just showing here that the concentration of A is going down and the concentration of BC is going down as the reaction takes place. And the concentration of AB and the concentration of C go up. So you can see by this point, the rate of the reaction in the reverse direction has increased by this much. And then if we move forward in time and we take another snapshot, the rates are converging because the concentration of reactants is going down and the concentration of products is coming up until we reach this point right here, which is equilibrium.